Thanks, Daryl. Yeah, thanks everybody for coming and for inviting me. I've had a really great time so far. Talked to many of you. And yeah, I'm going to tell you about cosmology and fundamental physics from stellar mass binary black holes. Before I move off my title slide, you might have noticed that every LIGO paper is Abbott et al. And so it's very helpful to have links to which Abbott et al. I'm discussing. This QR code will lead you to these slides, and you can click the links and see which paper I'm talking about when. I'll throw it up again at the end if you didn't snap a picture. So in this audience, probably it's not needed, but I'm still going to do it. I'm going to give you a little orientation of the LIGO instrument, the experiment, what it is we measure. And at a fundamental level, we measure gravitational waves. Gravitational waves are propagating distortions in space and time. You can measure them by doing metrology. In particular, if you have an interferometer, LIGO is an interferometer. It's actually two interferometers. Schematically, that's a laser sent through a beam splitter that propagates down two arms. And as the length of the arms changes, maybe because the Earth is moving, or maybe because the gravitational wave is passing through the interferometer, different numbers of cycles fit in each arm, which means the interference when the light is recombined at the beam splitter changes the output intensity. Okay, that's how interferometers work. And this is a readout of the LIGO interferometer just sitting in 2015. It's described in this paper, which is actually the paper that describes the first detection of gravitational waves, GW 150914. The interferometer today has a similar sort of shape to this curve, but at a substantially lower level, thanks to technological improvements since 2016. If you just let the interferometer sit, you measure the fluctuating output here, convert it to a strain, so a fractional change in the length of the arms, and form a power spectrum, so how much variation is there at each frequency, you get a curve that looks like this. And so we're talking about sort of a strain noise, variation in the strain. The amplitude of that is 10 to the minus 23 per root hertz at 200 hertz. Okay, whatever. What does that mean? Well, the frequency, 200 hertz, is the gravitational wave frequency that would be emitted by two 10 solar mass objects orbiting each other about at the innermost stable circular orbit of a Schwarzschild spacetime. And the frequency of gravitational waves scales inversely with the total mass of the system. So 200 hertz means we are optimized to detect stellar mass compact objects. Tens of solar masses is ideal. What about the amplitude? Okay, so this is a little more subtle. And here, because this is an astronomical audience, I feel obligated to put in a little dig at electromagnetic astronomers. Electromagnetic astronomy, optical astronomy, X-ray astronomy, is a photon bucket, right? Essentially, you measure energies or photon counts. It's a destructive measurement. Our measurement is not destructive. We measure the gravitational field, right? No gravitons were harmed in the making of this measurement. That's not quite true, but very few gravitons are absorbed by our instrument. And what that means is we are actually sensitive to amplitudes, not energies. So an amplitude sensitivity of 10 to the minus 23, what does that mean? Well, the gravitational field H is a dimensionless quantity. These gravitational waves are produced in compact object mergers where the spacetime is highly distorted. So near the merger, the strain must be something that's sort of order 1. And then by energy conservation, the energy goes like the strain squared. The strain has to fall off like 1 over r so that the energy follows an inverse square law and the propagating wave conserves energy. But I need something that's dimensionless that falls off like 1 over r. I need something with units of length in the problem, and in gravity, the only thing with units of length is the Schwarzschild radius. So a useful estimate for the amplitude of your gravitational wave is some order 1 quantity times the ratio of the Schwarzschild radius of the system that made it to the distance at which you are observing. And if you plug in those numbers, 10 solar mass black holes making the wave, say, a gigaparsec distance, you get a strain of 10 to the minus 23 right there. LIGO is an instrument that is optimized to detect stellar mass compact objects at gigaparsec distances. Okay, great. And to complete the dig at electromagnetic astronomy, if this noise level drops by a factor of 2, we can see the same intrinsic strain to twice the distance, which is 8 times in Euclidean universe, the volume. The improvements in our sensitivity accumulate more rapidly than if we were a graviton bucket, where we would get a factor of 2 to the 3 halves instead of 2 cubed by doubling our sensitivity. And you'll see that over the next few slides as I show you the progression of LIGO catalogs. Starting in 2019 with the gravitational wave transient catalog 1, we had 10 sources. Right about here, this one is GW 150914, the first one. That little red dot that you can barely see is a binary neutron star merger. I'll discuss that in a minute. We have a bunch of other black hole sources, which are tens of solar masses at gigaparsec distances, as I just described. So GWTC1, we have 10 sources. That catalog paper is published in 2019. A year later, we published our second catalog, which actually incorporated the first 3-ish observing runs, and we have 35 sources. Again, they occupy masses that are sort of tens of solar masses. This is the mass ratio. Many of these systems are consistent with equal mass, but some of them are not. We have our first, what seems to be black hole neutron star mergers, black hole merged with something that could be a neutron star, maybe a little too heavy. And then a large number of binary black holes and another binary neutron star merger. Fast forward another year to the second half of the third observing run, we get another 35 sources. So now we're talking about 70 sources in total. This is the rapid R cubed improvement as our sensitivity comes down. And as we speak today, we are in the midst of our fourth observing run, 04. The most recent event when I made this screenshot this morning was 241116 from about 4 days ago. It was probably a binary black hole. It lived in some region of the sky that's fairly large, far too large to point an optical telescope at efficiently. Over the course of the last year or so of the fourth observational run, we've got an additional 160 candidates. We'll be deep into the 200s by the time this run concludes. Presently, we're detecting black holes, binary black hole mergers at the rate of about 1 every 3 days. The overall rate in the universe is about 1 every 30 minutes. So we have a long ways to go. However, we are currently seeking funding and devising plans for the next generation of gravitational wave detectors, which will improve the sensitivity by about an order of magnitude. If that's realized, we will see basically all the binary black hole mergers in the universe. So by the mid-2030s, we could be detecting 1 binary black hole every half an hour. Okay, what can you do with these sources? Well, each source is an interesting and special thing in its own right. They all tell you something about their progenitors, their massive stellar progenitors. I'm not going to talk about that today. I am going to ruthlessly exploit these sources as probes of other things. The first other thing that I'm going to probe is cosmology, or let's say cosmography, measuring the expansion history of the universe with LIGO sources. In contrast to electromagnetic astronomy, in our situation, distances are easy for us to measure for the following reason. There is a constant of nature, c to the 5th over g, which is a luminosity of 3 times 10 to the 59 ergs per second, 1 million or 10 million times the luminosity that's achieved in a supernova. There are no, these are constants. This is a universal thing. This is up to factors of, a few percent out here, the luminosity in gravitational waves at the end of a binary black hole merger of any mass. And the reason for that is the energy that's emitted in a black hole merger is some fraction of mc squared. That scales with the mass. But the orbital timescales are the speed of light going around at near the Schwarzschild radius. That orbital timescale also scales with the mass, and the mass cancels out. So we have standard candles by default. For us, it's redshifts that are hard, okay? In gravitational wave astronomy, we measure masses by tracking the frequency evolution of the signal. The heavier the system is, the more rapidly it chirps from low frequency and large separation through to high frequency and merger. But because we measure masses from frequencies, gravitational waves, just like any wave, redshift as they propagate through cosmological distances. So the frequencies that we observe at the detector have been redshifted. The masses that we calculate at the detector are the bare masses, the rest frame masses, redshifted by 1 plus c. So for us, it's the inverse situation to doing, say, optical astronomy, where a spectrum can easily give you redshifts, but it's hard to calibrate luminosities and understand distances. Okay. Oops. I wanted to say, so on the other hand, if someone rang you on the phone and told you that the black hole that you just saw merged was a 30 solar mass object merging with a 40 solar mass object, if you knew this, then measuring that gives you a redshift. And we'll come back to that point in a couple slides. Okay, the easy way to do cosmography with gravitational waves is to use the gravitational waves to measure distances and have some kind of electromagnetic counterpart that you can use to measure redshifts. Combine those two, you can get the Hubble relation, you can measure the expansion history of the universe, et cetera. This was famously done for GW 170817. Here is a plot of the gravitational wave Hubble diagram, distance in megaparsecs here. The event was like 35, maybe 40 megaparsecs away. So this error bar is coming from the gravitational wave measurement. But there was a kilonova counterpart in a galaxy. The redshift to the galaxy has been measured. If you convert that to a recession velocity, it's here, just a little under 3,000 kilometers a second. Those two measurements together give you the slope of this line, which is the Hubble constant, okay? Compared to the original Hubble plot, which it goes down here in this corner. That may have been done for one other system. Matthew Graham and collaborators here suggested that there might have been a flare in an active galaxy associated with another merger that we saw, GW 1905-21. If you use the redshift of that galaxy and the distance we measured in 1905-21, you can combine those two measurements and get a curve that looks like this blue curve, which is slightly better than GW 1708-17 alone, but still not interesting in terms of the Hubble tension, which is a current problem in cosmography, where measurements of the Hubble constant from the early universe or from present-day properties derived from the early universe differ dramatically from measurements based on a local distance ladder. Okay. What if, though? So this is cool. This is great. It's lovely. The paper describing this came out in 2017 because that was the last time we had a neutron star merger with an electromagnetic counterpart. Everyone is on tenterhooks. It sure would be great if we had more, but they aren't exactly rolling in. Sorry, we're doing what we can. What can you do in the interim? Okay, well, how can you get redshifts without electromagnetic observations? As I said, if someone told you the mass of your merger, then measuring this tells you the redshift. And this is an old idea. It goes back to Chernoff and Finn from the 90s. In that case, and also in Taylor and Gare 2012, which was sort of an update on this original paper, the picture was that neutron stars are all about 1.4 solar masses. So you don't actually need a phone call. If you can measure neutron star mergers at cosmologically relevant redshifts, you can say this is about 1.4. This tells me the redshift. I can do cosmology. That has the same problem that we're facing with neutron stars and counterparts, which is the neutron stars are just not rolling in. Is there something we can do in the interim? It turns out there might be. Okay, so after our very first catalog, 10 sources, 10 binary black hole mergers in LIGO, Maya Fischbach, who's now at the University of Toronto, this was when she was a beginning PhD student with Dan Holtz at Chicago, wrote a very influential paper. The title is Where Are LIGO's Big Black Holes? At the time, we had a catalog of 10 binary black hole mergers, and our estimates of their total mass are just plotted here. And you can see that even the most massive of them maybe was a total mass of 60 or potentially 70 solar masses, but not heavier. If you ask about LIGO's sensitivity, LIGO should easily have been able to detect mergers with 100 solar masses of total mass, so a 50-50 merger. In fact, to nearly twice as far, or a little bit more than twice as far, as it can detect sources here at 75. So where are the heavy black holes, right? Where did they come from? We're even more sensitive to these systems, but we've seen 0 of them while we've seen 10 of these. There must be some physical process that prevents big binary black holes from forming and merging. And in fact, there is such a process. I'll come to it in a few slides. It was proposed as a potential explanation of these missing massive black holes. It doesn't quite work for reasons that I'll explain in a minute. But if you just take it as a given that there's some natural process that truncates the black hole mass function somewhere, that's not quite as good as being told what the mass of every source is, but it does introduce a mass scale into the black hole mass function. And that mass scale will redshift, right? This system was not observed in the detector at 45 or 50 solar masses. It was observed in the detector at 65, 70, 80 because of the redshifting effect. Effectively, we have an absorption line or an absorption band in the black hole mass function. And so I wrote a paper with Maya and Dan that pointed out that you could use this to do cosmography. We built little toy models. This is a toy model of a black hole mass function that looks like a power law with a truncation. There's some smooth decay, and because we had estimates of where that had to be, we put it at about 45 solar masses in the rest frame. But if you now imagine a bunch of black hole mergers, the blue dots here are sort of what you might get in 1 year at design sensitivity. So a few years from now, 1 year of advanced LIGO running. The orange dots are what you'd get in 5 years at design sensitivity. So you run the thing into the early 2030s. At these cosmological distances, the redshift is significant. So something that is 45 solar masses in its rest frame, you put it at 10 gigaparsecs and we observe it as a 100 solar mass black hole. You can see, though, that there's an edge to this population of sources. And if you can track that edge, its location is 45 times 1 plus z as a function of d. That lets you do regression to determine the cosmological parameters of the universe, the Hubble rate, matter density, all the things that control cosmography. This is a simulation. We had true masses. If you put in error bars on the masses, the problem becomes a little bit harder because the measurements of distance and also of mass are significantly uncertain. But this is the kind of thing that we now know how to do in LIGO. We build big hierarchical statistical models to determine our uncertainty about where the edge is given these error bars and these observations of sources. And if you do that, it turns out that you can measure the expansion rate in 5 years of LIGO data to something like 3%. Now, you don't measure the Hubble constant directly. People often say, oh, you can measure the Hubble constant this way. It's true that you can, but it's not actually optimized for measuring the Hubble constant because most of your black hole mergers are not local. They're out here at redshift 0.5, 1, 1.5. So in this particular setup, we measure the Hubble constant to 3%, or the Hubble, the expansion rate to 3% at redshift 0.8. But that's fine. There's supernova data sets that can connect redshift 0.8 to the local universe. Basically, this provides a calibrated distance ladder to redshift 0.8. And then you can move that around however you want in galaxy surveys looking for the baryon acoustic feature or whatever. So 3% at redshift 0.8 translated to H naught is 2 kilometers per second per megaparsec, which is not as good as the best present day measurements, but certainly good enough to distinguish between the local distance ladder and the early universe distance ladder. Okay, well, this was all done when we thought that there was just missing black holes at high mass with 10 sources. Today we have 80 sources. What does the mass function look like now? This is what the mass function looks like. There's various different models that have been fit to the mass function. This is from the most recent LIGO population paper, and each of these curves is a different parameterized or semi-parameterized model of the mass function. This is another semi-parameterized model. This is a paper that I wrote with Tom Callister a year ago, where we used, well, I guess it's non-parametric, or maybe it's infinitely parametric. We used a Gaussian process, so a smooth function, to fit the mass function of black holes. But you can see there's a lot of structure here. All of these models uncover certain structure. First, there's a global peak at 10 solar masses in the merger rate, and the merger rate falls to either side. We don't really know why that's the case, by the way. There are some models that can produce this, but it's not terribly well understood, predicted from first principles in any sense, that there should be a peak in the merger rate at 10 solar masses, but there seems to be. Then the merger rate declines, and maybe declines or stays flat through 20 and up to sort of 30 solar masses. Then there's a feature at 35 solar masses, a peak here in the merger rate. And then it declines further for those missing black holes that Maya noticed. They aren't actually missing anymore. We have a handful of sources out here in this high mass region. But definitely far fewer mergers here than there are here at low mass. All of this structure is something that you can latch onto for doing cosmology. Now, I've painted a pretty rosy picture for you, and maybe you're asking yourself now, well, if you want to track, say, this bump here at 35 solar masses as a measure of the redshift of your sources, it had better be the case that over cosmic time, that bump stays in the same place in the rest frame, right? If the types of mergers that occur are changing over cosmic history, and we know, for example, that the metallicity of stars that are forming is changing over cosmic history, that can certainly have an effect on the properties of binary evolution. If that's the case, how could we possibly know that this 35 solar mass bump stays at 35 solar masses in the rest frame and therefore is a good measure of redshifts? Well, we don't. None of these features are predicted from first principles. However, for a time, there was plausible to do with a feature of massive stars called the pair instability. So here is a paper by Rob Farmer, who is a stellar modeler, and he's reporting on models of massive stars. These are stars with a carbon-oxygen core mass, 30, 40, 50, 60 solar masses, so total mass that's maybe considerably higher, maybe even double that in some cases. They're in binary, so you imagine that the outer envelope gets stripped and you're left with a carbon-oxygen core of these masses, and you evolve that core and predict what the black hole remnant mass should be. And here, when the mass of the core is 20 or 30 or 35 or even 40 in these models, the heavier the core gets, the heavier the black hole gets. That's straightforward. It's very sensible. At some point, though, that relationship softens. What's happening at this transition is that as the core gets more massive, its central pressure and temperature rise. And right around here in these models, the central temperature is getting within spitting distance of 511 keV. So the photons that are providing radiation pressure support to the core, the very high energy tail of their thermal distribution, is able to pair produce. Photons collide, electron-positron pairs come out, and the pressure of the core drops. As the photons provide relativistic pressure, the electron-positron pairs are produced, at rest or nearly at rest. And so you lose pressure support in the core collapses and initiates explosively nuclear burning at some point. So it collapses, heats up, ignition, explosive burning, and that drives a shock through the star. Right at the onset of that shock or pulsation, there is some mass removed as the shock gets close to the surface. It steepens, blows off the outer layers of the star. It's not quite energetic enough to blow the whole thing up. But now that you've lost some mass from the outer layers, when the star settles down again, the core temperature and pressure are below the level of the instability, and they slowly grow again. Maybe another round of instability, another pulsation. These objects can go through several rounds of these pulsations, losing mass each time, until they have lost enough mass that they no longer participate in the instability. That leads to this softening in the initial final mass relationship. This whole wide range of initial masses accumulate at a remnant mass, which is the remnant mass that is the onset of the instability. If your core is sufficiently massive, that first explosive burning has enough energy in it to disrupt the star or to remove a huge amount of mass. And so at some point, you just blow the whole thing up in what's called a pair instability supernova. It's possible there have been a few pair instability supernova observed. Observers argue about whether the properties of these strange supernova are consistent with the pair instability expectation. Who knows? However, the principles of this process are pretty robust. Calculating the central pressure and temperature from hydrostatic equilibrium is like a first-year, graduate stellar structure problem. It's not terribly sensitive to the details of the star. Pair production when photons reach 511 keV is, not a terribly complicated thing. So, this is as close to a first principles prediction of some kind of upper mass threshold as you can get in astrophysics. Great. Still, maybe you don't want to build complicated stellar models. Maybe you want something that just matches the schematic features of this. And if you do, you should ask Jacob, who is right there in a pink shirt. Jacob, Max Easy, and I wrote a paper last year that built simple models of this process and the effect that it would have on the black hole mass function. So down here, you see something that looks like a featureless IMF. This is like a saltpeter IMF. It's a plain power law. There's no mass scale in it. Here is a simplified model of this initial final mass relationship that is linear up to a point, turns over, reaching a maximum, and then plummets to zero. And when you pass the featureless IMF through this initial final mass relationship, because there's a finite range of masses here that all map to the same remnant mass, you get a bump in the mass function. But you don't just get any bump. The properties of the bump are related to the structural parameters of this initial final mass relationship. For example, if you change the mass at which the pulsations turn on, the location of the bump moves to the right. But because the IMF is lower at higher masses, the peak of the bump also shifts downward. Right? You don't have complete freedom to shape the peak. Similarly, if you change the maximum mass that is achieved before the relationship completely turns over, you don't shift the onset, you shift the location of the peak and you change its width and its prominence. Right? In this simplified model, there's structural parameters shape of the peak. And so you could imagine fitting those structural parameters, right? Measure the shape of this peak over cosmic time and ask, is the shape of the peak consistent? Is the process, the initial final mass relationship that produces this peak, the same over cosmic history? If it is, great. Now you stand a chance of using this peak to measure redshifts. If the process that produces the peak is changing over cosmic history, then you have to find a way to calibrate that out or otherwise understand it in order to use this as a measurement. And we already can see, when we fit models that have these sorts of shapes built into them, we can see that there is a definite shape to the peak in the existing catalog. The peak that we find has a characteristic width, a peak in a certain spot, an onset at a different spot, and a decay that is fairly steep. We can't yet see, to any measurable or reasonable precision, whether the shape of the peak is changing in redshift, but we only have 100 sources. When the next catalog drops, we'll have several hundred sources. The precision of this measurement improves all the time. Okay, besides calibrating the location of a peak by confirming that its shape isn't changing over cosmic time, you can also calibrate different pieces of the mass function against each other, right? There's not just a peak here at 35 solar masses. There's also a peak here at 10 solar masses. There's a decay over here. So Jose Ezquiaga and Dan Holtz asked, what happens if you just latch on to this peak and this peak? Now, if something is happening in stellar evolution that moves the 35 solar mass peak, these objects have a completely different evolutionary history. Why would this peak move in the same way that the 35 solar mass peak is moving? So you can calibrate the redshifts of the two peaks against each other. They did exactly that. The 10 solar mass peak is not so good in our present instrument because we can't really see it to cosmologically relevant distances. Those black holes are too quiet. But if you imagine third generation gravitational wave detectors, so something in the mid 2030s, the next generation of instrument, if you leave it running for a month, you collect tens of thousands of binary black holes. Once you've collected tens of thousands of binary black holes, some of them are in the 10 solar mass peak, some of them in the 35 solar mass peak, you calibrate your cosmology by measuring redshifts with those peaks, and you get an uncertainty on the expansion rate that is this blue curve. These green bars here are the eventual measurement precision of the DESI instrument. And you can see that a month of 3G data gives you better constraints on H of Z than all of DESI. 3G is also cool for neutron stars. If the 10 solar mass peak can't today be seen to cosmologically relevant distances, neutron stars certainly cannot. Our neutron star horizon is redshift of 0.0 few. Okay, so not relevant for measuring the expansion history. But third generation detectors, the neutron star horizon is redshift 2. So now you get hundreds of thousands of binary neutron star mergers every year. You can play the original Finn and Chernoff game, right? All binary neutron stars are 1.35. That's not true, but pretend that all binary neutron stars are 1.35. Use that to measure redshifts. And you have so many sources that you can achieve percent level precision, say in the Hubble constant, with merely 20 days of observing time, provided that the mass function of neutron stars does not also evolve with redshift. So this paper by my graduate student, Shimendra Roy, and a postdoc at CCA, Lika Van Son, looks at our best guess for the population of neutron stars from various population synthesis models and asks, what would happen if you simply ignored redshift evolution and fit the mass function with a distribution that was just constant in cosmic time? And the answer is that at least until you're well below percent precision, you don't get systematic biases. So our best guess at the formation scenarios for merging binary neutron stars today predict a very redshift independent mass function, and so suitable for percent level precision in cosmological measurements. Time will tell whether those predictions are right, but that's our best guess. Okay, now I'm going to switch gears. So for the last half an hour or so, we've been ruthlessly exploiting black holes as probes of cosmic expansion. Now I would like to ruthlessly exploit black holes as probes of extreme spacetime and the theory of gravity. So I want to talk about ringing black holes and probing GR in the strong field. And I want to motivate this with a mathematical question, a famous mathematical question that was posed by Katz in the 1960s. Can you hear the shape of a drum? So the idea is, if you think about instruments, right? You play a trumpet, you play middle C on a trumpet, it sounds like one thing. You play middle C on a French horn, it sounds like a different thing. You play it on a violin, it's yet different. Even though the sort of fundamental frequency is the same, the spectrum of the instrument is different. So Katz was asking, if you know the spectrum of an object, like a drum, can you predict its shape? That is, are the eigenvalues of solutions to Laplace's equation in 2D uniquely specifying the boundary? And the answer is no. Here are two drums that you can find easily on the internet that have exactly the same eigenfrequencies, but they have sharp edges. So if you talk about real physical drums that don't have kinks in them, the answer is actually yes. Okay, great. That's cool for drums. What about atoms? You absolutely can see the shape of a hydrogen atom, if you'll permit me to be metaphorical here, right? If you do atomic spectroscopy, this is the Lyman series of spectral lines. And even before we had quantum mechanics, it was known that their inverse wavelengths followed a simple numerological relationship. There was a dimensionful constant out here, the Rydberg constant, and successive lines followed this pattern 1 minus 1 over n squared. Okay. In modern times, we understand that this piece, the Rydberg constant, involves fundamental constants that are related to the sort of structure of hydrogen. And then quantum mechanics predicts this sequence of eigenvalues of the Hamiltonian for a hydrogen atom. Okay, great. How about black hole mergers? All right, let's see if this is going to play, and if it doesn't, we'll just move on. Nope. Maybe not. Okay. There we go. Good. Here's a video of the black hole merger from my colleagues in the SXS collaboration. This particular system was set up to look like GW 150914. So the two black holes are nearly equal mass. That's a very common merger for LIGO to detect. You can see here they're in their last half a second of life. They're getting quite close to each other. But at this point, they are still two independent black holes. They have separated horizons, right? As the orbit shrinks, you can see the amplitude of the waves is getting larger. The frequency of the gravitational wave is also getting higher. And in a moment here, we're going to come to a place in the simulation where the two horizons touch. And the object is going to go from being two black holes to being a black peanut. Now, you may know or be aware, or I'll just tell you, that the stable final end state in general relativity of a system like this is a Kerr black hole. The system will get from black peanut to Kerr black hole by radiating away all of its peanutness and settling down into a final Kerr state. That final radiation is called the ringdown. And if you have sufficient coffee and stamina, you can calculate, using perturbations to the Kerr metric, what the eigenfrequencies of that ringdown look like, the quasi-normal modes of the Kerr solution. The radiation right at the end of that simulation is coming out in eigenfunctions that have definite frequency and damping time. They have a complex frequency, in other words. And this is, there we go. This is now a 50 or 51-year-old field, including some of the first numerical calculations of the normal modes in Schwarzschild spacetime. Famously, Tucholsky deriving the Tucholsky equation that describes perturbations to occur spacetime, calculation of the eigenfrequencies, the idea that we might do black hole spectroscopy, right? Spectral lines in black holes and gravitational waves, just like spectral lines in atoms. And of course, thousands of references up to the present day. Now, one crucial distinction is, unlike a musical instrument or a hydrogen atom, black holes are really crappy resonators. So the picture you should have in your head is not a ringing bell, which will go for thousands or tens of thousands of cycles before it decays, but something with a quality factor of 2 or 3. So they actually kind of sound like that: thunk, thud, splat. Nevertheless, black holes have normal modes. And somewhat surprisingly, there was sort of a revitalization of this field in 2019 when Matt Giesler, who at the time was a graduate student here, working with Saul Tucholsky, pointed out that black holes seem to behave like bells or perturbed Kerr spacetimes way earlier in their evolution than they should. So this is the end stages of a numerical simulation of a black hole merger, just like the video that I played for you. And this point right here is the peak of the gravitational wave strain. And roughly, time is not a gauge invariant quantity, but roughly corresponds to the point at which the black peanut starts forming. At that point, locally, you do not have a linearly perturbed Kerr spacetime, right? It's a peanut. It's not a tiny perturbation on the Kerr ellipsoid. However, the emission from that point on looks very much like a sum, in this case, of 7 normal modes. That's the orange dashed line. You can see it's almost a perfect fit, which are a fundamental mode and 6 overtones. In black hole spectroscopy, the overtones are more rapidly decaying modes at almost the same frequency, but with much higher decay rates. So the fundamental has a quality factor of a few. The first overtone has a quality factor of 1 and a bit. The second overtone doesn't even oscillate, it just dies, and so on and so on and so on. And the reason this was a revitalization was, if it is the case that the signal looks like a superposition of normal modes right from the peak of the strain, then you can start looking for those normal modes from the peak of the strain, rather than waiting until almost all of the peanutness is gone and you just have a locally perturbed, like linearly perturbed Kerr solution way late here. And since the modes are decaying exponentially, going to earlier times gets you a lot more amplitude in the modes and a lot more sensitivity in the measurement. It's still argued, it's very much a matter of contention in the literature, whether the black hole system is really behaving linearly at that time. In some ways, it almost certainly is not. In other ways, it is. For example, if you look at the 7th overtone and you ask, okay, let's suppose that it was the 7th overtone of a Kerr black hole, but with varying masses and spins away from the true value. What is the best fit to that waveform? The best fit to that waveform localizes the 7th overtone in the place where it's supposed to be. Okay, great. Other analyses, this one by Vishal Baimov, have, suggested that maybe once you get past the 2nd or 3rd overtone, actually the best fit mass and spin are not quite the right mass and spin. However, the difference in goodness of fit between this place and this place would require a signal that has signal noise ratios in the thousands or tens of thousands in order to tell the difference in real LIGO data. So this is a very active area of theoretical investigation, including on today's archive. Matt Giesler, in collaboration with a bunch of folks, including Keith Mittman, who sometimes sits at CCA in our group, published a paper showing the amplitude time evolution of this whole suite of modes in a simulation. And they certainly look like they're just decaying away, just like sourced normal modes should. The debate continues, but it is absolutely the case that in present LIGO noise, where the signal-to-noise ratio of ringdowns is of order 10 or maybe 20, these kinds of fine distinctions are simply not possible. So if you take a two-tone model, a fundamental mode, it's shown up very faint, shown here in blue, it's long-lived, and its first overtone, short-lived in yellow here, they combine to make the purple. And you put them into the Hanford and Livingston LIGO detectors at a reasonable signal-to-noise ratio. I think this one is 20. And you fit this model with two overtones, you can extract the remnant mass and spin, as if the model was perfectly in the linear regime and described by this sum of damped sinusoids. And in fact, Max Isi and Matt Giesler and I and Saul Tukolsky and some other folks did this for the very first detection, GW 150914, a few years ago. We find in Livingston and in Hanford that in order to fit the signal well, we do need a fundamental mode and an overtone. Okay, so there definitely seem to be two tones in this data. And in fact, they combine in about the right phase relationship that you might expect from a merger. The fundamental and the overtone cancel each other early and then dephase. And when you do that, you can ask, is the overtone in the right place to be consistent with a Kerr spectrum? Right? I measure the fundamental mass, the fundamental frequency and damping time. That tells me the mass and spin of the black hole. I predict where the overtone should be, and I ask about whether we measure it with a frequency offset or a damping time offset. And the answer is it is totally consistent with being right where it should be. Its damping time is very uncertain, sort of at the factor of 2 level, but its frequency is not. Its frequency matches the frequency you would expect to about plus or minus 20%. Great. We should do this again. A good choice to do this again is a signal GW 190521, the most massive signal that LIGO has seen. This signal is almost all ringdown. There's very little in spiral to it. But it has a complication. it's very likely that this system was precessing, by which I mean that the individual black hole spins in this system are not aligned with the orbit. An aligned system like this does not precess because there's a single axis in common for the orbital angular momentum and the spins, and therefore the total angular momentum. And that is the same axis as the remnant black hole that is formed. If, however, the spins are misaligned with the orbit, then the total angular momentum points in a different direction, and the total angular momentum near the plunge is just about the angular momentum the remnant has when it finally settles down, and so the remnant axis is tilted with respect to the orbital axis. This turns out to have interesting consequences. First, if you just look in the data, so this was a paper by Harrison Siegel, who's a graduate student of mine from Columbia. It's actually a graduate student of Yuri Levin, but Yuri's put him on loan to Max and me very kindly. And so he works with us a lot. If you try to measure the final mass and spin of this system, you discover that you can't match the mass and spin that we measure from complete waveform models, doing sort of extraction with actual numerical relativity waveforms, unless you include a 2-2 fundamental mode and also a 2-1 fundamental mode, so a mode with a different spatial pattern, like a 2-1 YLM. That is simply a statement about data, but it came as rather a surprise to us because most people thought that in systems like this, the 2-1 mode would not be highly excited. What's going on? Oh, yeah. If you then ask, is the 2-1 mode where it should be? Again, it's in the right place to about plus or minus 20%. So we now have two 20% measurements of the Kerr spacetime. Okay, so what's happening here? Well, it turns out Harrison had an idea as to how the 2-1 mode could get excited. And it has to do with this misalignment angle between the remnant axis, where the modes are defined, and the orbital axis, which is where the perturbation is set up. So the peanut shape, right? The peanut shape is going to be aligned along the orbit of the black holes as they merge. But the definition of the modes occurs in the remnant frame. Now, the peanut is absolutely a 2-2 spherical harmonic type of perturbation. Okay, if you decompose that in spherical harmonics, it's basically all 2-2. However, the perturbation theory is done in a rotated frame. So if you take a 2-2 source in the orbital frame and you just rotate it into the remnant frame, you can calculate how it decomposes into spherical harmonics in the remnant frame. Okay, so that's what's shown here. This is the ratio of the 2-1 amplitude to the 2-2 amplitude. The black line here is just the Wigner-D matrix component for the rotation that you should be doing based on the misalignment angle between the remnant and the final orbit. Each of these dots is a numerical relativity simulation from which we have extracted mode amplitudes. And you can see there's some scatter. The relationship is not perfect. It's not purely a 2-2 perturbation that gets rotated into the remnant frame, but that describes the bulk of the excitation of the 2-1 mode, and then over here also the 2-0 mode as a function of misalignment angle. And this very simple physical picture gives some insight into how the modes are sourced right at merger, and also holds some promise for maybe improving waveform models that try to phenomenologically stitch some merger ringdown piece into an in-spiral piece that is calculated in a different way. Okay, so that was very exciting. Ultimately, what we have is two measurements that the Kerr prediction for the ringdown of these black holes is correct at the 10-20% level. We're hardly doing precision spectroscopy yet. This is more like, you know, you throw sodium into a flame and you get yellow, right? This is kind of the level that we're working at. But we have a ton more sources coming down the pipe, and each time we do it, we get more and more precise. One day, perhaps, we'll be at the level of actually doing this sort of atomic spectroscopy. If you want to ask me about other cosmological tests, that's fine, but I'm not going to talk about them now because I'm running out of time. So I'm just going to say thank you. If you want to get the slides, there's the QR code. Yeah. But it seemed like you thought that one. Yeah. It turns out, so it's such a cute explanation with one little problem. And that little problem is that if you ask sort of at what mass the pulsations ought to set in, you can see here it's about 45 solar masses. But the peak is at 35 solar masses. And it's very hard. So where the pulsations happen depends a little bit on nuclear physics because it depends on the core that gets built up. So you can play with nuclear reaction rates and change the core structure a little bit, but basically there doesn't seem to be any way to change the core structure and get this peak to happen at 35 solar masses, unless we really don't understand about how the pulsational mass loss happens or some other feature of the cores of these stars. So the pair instability was a cute explanation, but doesn't probably work for the 35 solar mass peak. If you not, maybe you understand where the happen. Absolutely. Yes. So, yeah, so the way the pulsations are done, for example, you may know where they turn on, but the calculations are either like 1D hydro in a 1D stellar model, and the shock steepens and breaks somewhere and deposits its energy, and then you ask, does that like lift everything above it off the star? Yes. Or they're 2 or 3D shock propagation in a tube or a stratified atmosphere, but not actually the star. And so, trying to calculate exactly the hydro of this is hard. So maybe this comes down here. On the other hand, also, there are lots of other processes in stellar evolution that have the generic feature that they remove mass at an increasing rate as you get heavier. So this is hardly the only thing that could give you this picture of a linear relationship that softens and produces a peak. I think the jury's out. We really don't know. But at least if we can measure structural parameters, we can calibrate it well enough to do cosmology. I mean, where do 1As come from? I don't know, but we use them pretty well. Right. So it's kind of, we're sort of in the same picture where this is just going to have to be an empirical calibration, I think. Yep.
Is there any other than that, is it consistent?
There's several layers to that question. At a bulk level, it's basically consistent with what you expect from simulations of mergers. In particular, the phase relationship between the fundamental and the overtone, and the phase relationship between the 2-2 and the 2-1 are not incredibly well constrained in the data, but are measured reasonably well and match what you get from simulations. If you think about, mapping initial conditions, I need up to a total mass, which is 3 scales everything. I need 7 parameters to describe my initial binary orbit if it's circular. By the time I have 2 ring down modes, each one has an amplitude and a phase and 2 polarizations. So each mode carries 4 degrees of freedom. 2 times that is 8. So I actually have more freedom in arbitrary modes than I do in my initial conditions. So there are lots of constraints in the excitation of the modes that must be present. Work is underway. Keith Mittman, for example, is spending a lot of time thinking about how to parameterize the constraints that result from these in-spirals on the amplitudes and phases of the mode excitations. That's been studied in Schwarzschild sort of extensively, but less so in Kerr. That's kind of the frontier of where we're at.
It's really, if you think forward to third generation.
Oh yeah, in third generation LIGO, we should be able to measure way more than 2 modes, at least for loud signals. We'll have the phase relationship between them. We can check that consistency with GR. Another thing that we can do in the near future, I said there's 7 parameters for a binary in-spiral. That's a quasi-circular binary in-spiral. If it's eccentric, you add a few more parameters. And we no longer have good waveforms that have been calculated to acceptable levels of precision that incorporate precession and eccentricity. However, if you just look at the ring down and you see mode excitations that look weird, that can be a hint of eccentricity that doesn't rely on having a parameterized waveform to do the calculation. It's merely, this doesn't look like a quasi-circular in spiral. And so in some sense, examining the ring downs of systems that are weird in that way could be more robust than trying to fit, poorly modeled waveforms that, don't actually include the relevant physics to sufficient precision to extract, say, precession and eccentricity. That's right.
But interesting that it from
That's right. So where am I? I'm looking for the Giesler paper, which is here. So yeah, in fact, in this case, something like a few percent, 5% of MC squared comes out. But the key is these ring down modes are the ring down modes of the final state remnant. Right? You would not want to, well, you could, I suppose, as a phenomenological model, imagine a time evolving mass and therefore time evolving frequencies and damping rates. That's not really linear perturbation theory. That might be an effectual waveform, fine. That's always acceptable to do. The thing that surprises people is that using the remnant mass and spin, you can use the purely linear prediction for the waveform back so long. That still radiates away a significant amount of energy. That's fine. It's merely radiating away the perturbations, which carry a significant amount of energy. But somehow, magically, even though the local spacetime is not linearly perturbed, what comes out matches the linear perturbation theory to like very high accuracy. And I don't think that's understood terribly well. Mm-hmm.
that feature seems like it's pretty robust. They're like a turn on.
Well, I mean, we've now seen famously just this year in a paper, right, a sort of 345 solar mass black hole. And so they're hard to detect, and we've seen ones, so they're actually pretty common. I mean, sure, I could make a story like that, but I could also make a story. In fact, Lika, the postdoc that I work with sometimes at CCA, has an explanation for why this drops at the left-hand side that involves when mass transfer is stable versus unstable in these low mass systems. If that's the case, then okay, maybe that's pretty robust because the dominant parameter that controls that is the mass ratio, and therefore it doesn't really change much over cosmic history. But stability and instability of mass transfer absolutely depends on stellar structure. And that can depend on things like metallicity that evolve a lot over cosmic time. So if you spin that story, this left edge of this peak might move around by 10 or 20% as you go from, the present day back to redshift 2 or 3. If that story's wrong and it's something else, who knows, right? So, in the end, it's sort of like we don't necessarily need to settle the question of what makes 1As if we can show that they're stable over cosmic time. In the same way, if we can show that these peaks keep their shape, don't move relative to each other, structural parameters stay the same over cosmic time, then we can set aside those very interesting astrophysics questions and just exploit them for cosmology. That's essentially the pitch I'm making. Though half the time I wear the astrophysics hat and I'm very curious what actually makes them. That's a fun question too, just not right now. So as a mechanical matter, it's true that our catalog contains source frame masses. And they are produced in the LIGO reference cosmology, which is something very close to what AstroPi thinks the Planck 2015 results were. Yeah, insiders are chuckling now because it's actually not exactly that for stupid reasons. But you could immediately undo that to produce estimates of the detector frame masses, the redshifted masses. And those are actually what's measured. And once you have done that, then you can apply any cosmology you want. So another way to think of this measurement is you can see here's luminosity distance, which we measured directly because we know the luminosity of the source and we measure fluxes. Here's detector frame masses, and there's this like sloping curve of sources. As you pick cosmologies, you are picking relationships between luminosity distance and redshift. And you are trying to cause the sloping banana of sources there to become flat and have a common mass scale at which they taper and vanish to nothing. That was in this measurement. If there was a peak, you'd see an overdensity of sources that describes some curve here. You'd adjust cosmology until that overdensity of sources lies flat in the source frame as a function of redshift. That's intuitive. Does that make sense? Yeah. 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 Cool. Yeah. Yeah. Thanks again.